This is getting set up. Okay, so I'm going to go ahead and hand it over to Dr. Kim Duffy, our host for the day. She's our Senior Product Manager for Life Sciences. You may have seen her on some of our previous sessions. If you are curious about any other sessions we've had, I think we've had around 30. They're all on our YouTube channel, youtube.com/Vicon, where this one will be afterwards. But with that being said, you can message me any questions if you have an upcoming topic or if you have any questions about things we're doing this year. And I'll go ahead and hand it over to Kim.
Hi, everyone. Thank you for the kind introduction there, Alicia. Today, we're going to be showcasing another Life Sciences Partnership webinar, and we're going to be talking about musculoskeletal modeling and how the AnyBody modeling system can be integrated with Vicon data. I'm pleased to be joined by the AnyBody team and Soren Torholm, who is one of the co-founders of AnyBody Technology and currently works as the head of services. Naturally, Soren is one of the more advanced AnyBody modeling system users, and his main working focus is on bringing the AnyBody human model into all sorts of applications, ranging from simple postures to complex movements. Soren will be providing an overview of AnyBody technology software, including applications, how this solution can assist with your musculoskeletal modeling needs. As mentioned by Alicia, there is Q&A available during this session, so feel free to either pop that into the chat or the Q&A, and we'll get it to the end. Over to you, Soren.
Thank you very much, Kim. So the outline for today is, first I will introduce you to the AnyBody modeling system, then I will introduce you to the AnyMocap model in AMMR. So the AnyMocap model is a model which is part of our novel repository. And after this introduction, I will introduce you to a new model library, which we have made available. This library is based on Vicon Nexus sample data set, and it displays examples on multiple lab settings in terms of marker protocols and force plate settings. So the idea behind releasing this model repository is that it can be used as an easy way for you to get started using Vicon data for doing musculoskeletal analysis. And after this, we will have a question and answer session. So first, a little bit about our company. So we developed the AnyBody modeling system, which is a tool for musculoskeletal simulations. Associated with the modeling system comes a full set of models, including both body models and application models, which brings these body models into life, into action. And all these models, they come as the AnyBody model repository. So we sell the license, we do training, we do support and consultancy services using these tools. And we are founded in 2001, so we have been around for more than 20 years. And as you can see on the image to the right, a lot of things has evolved over those years. The AnyBody modeler system is used for a wide range of application fields within biomechanics, but of course, in common for these fields is that it's something that the person is doing in a voluntarily and skilled manner. So it can be motion analysis, which what we'll cover today, but it can also be product design and optimization, sports, orthopedics, and rehabilitation, and ergonomics with and without exoskeletons, and automotive applications. Yeah, so it really a lot of different fields that these tools can be used in. The ingredients to a model like this is, first of all, of course, the body model. And it's fully parametric and scalable, and we then supply some motion and some forces to this model. And these motion and forces, they can either be simply measured, so by using a camera-based system, and the forces can be measured using force plates. And this is what we will show today. But of course, the forces, they can also be synthetically created using our software if they were not measured. So we will show you example of both measured forces and predicted forces. And finally, we supply some sort of environment around this human model. So in this case here, it's a lower extremity exoskeleton that is being part of the model. So we combine these ingredients into this one mechanical system containing both the human and its environment. And then we do the inverse dynamic muscle recruitment simulation to find the muscle forces that can create the dynamic balance in this mechanical system that is moving. So in the case of this exoskeleton model, it can calculate the, when we change the assistive torque on the model, it will automatically change the muscle forces, the muscle activations. They will change if we change the assistive torque. And then, of course, the reaction forces in the knee joint, for example, will also change. Once the analysis has completed, all this output is available and you can save it into different formats. You can also do a design optimization loop where you will optimize the model to obtain certain properties. But this is sort of the core of what we do, is that we impose motion to the model. We either predict the forces or impose measured forces, and then we find the balance in this mechanical system using muscle recruitment simulation. This slide here shows an overview of the body models in the repository. So there is a cervical spine model, a lumbar spine model, a detailed foot model, a leg model, and an arm model. And these body parts, they come together and forms a complete human model that can be configured in different ways. So you can switch easily between different type of muscle models. You can switch on and off different body parts if you don't need them, and easily configure these models in different ways. It's an open model library, meaning that it's written in a scripting language, so that you have full access to all the definitions of the muscles, the ligament, the bones, the joints. It's very detailed and validated, and there's been more than 950 papers published using these models. They can also be personalized using different type of data. So, for example, in this webcast here today, we will show you how the models are being scaled using the motion capture data. But it can also be scaled simply by putting in just height and weight. It's also possible to really to morph the shape of the bone into the shape of a subject bone. In terms of validation, these bar plots here, it shows a comparison with measured disc pressures in the lumbar disc, compared then with the compression force in the same joint of the model, and then this has been normalized for the standing posture, which is what you see here, and then the set of bars then represent the different load cases that we put this model into, and you can see it's possible to get a good match. Another kind of validation is what is shown here. So here the model is comparing measured knee forces against predicted knee forces. So there was a subject in the lab with an instrumented knee prosthesis that was capable of measuring the forces inside the knee, and then this Gait trial was then replicated in the simulation, and the force could be directly compared. Naturally, this is sort of a very sophisticated of model validation, and not something that can be done in everyday life, because these data is difficult to get. So usually what you can do is to compare predicted muscle activation and against the measured EMG. We have we are maintaining on our webpage a publication list that contains all the publications that have been made using the software and the models, and this can be categorized into different categories. And one of the tabs that you can press is the validation tab, and that currently then comprises 154 publications that is displaying some kind of validation comparing model results against some measured data. Now we come to the AnyMocap models in that is part of our current model repository. So it's a generic motion capture model which can be adapted to any marker protocol. It runs directly on the C3D file data, so it can optimize the location of marker locations and anthropometrics using optimization. And it supports, standard force plates of type 1 to 5. This type setting is normally something that is part of the C3D file when it's being exported. But if force plates are not in your lab setting, it's also possible to use to predict the ground reaction forces. I will show you examples of that. And these models, it's easy to handle, multiple subjects and multiple trials. This view here displays the AnyBody modeling system. So the section here in the middle is the scripting editor. And what I've loaded here is a main file of such a MoCap model. So we have here the first line here, the second line here is loading the trial specific data. So in the trial specific data, this is where you would specify the file name of the C3D file that you want to do the analysis on. This is also where you would specify the starting time and end time of the analysis and these kind of things. The subject specific data, this is where you will enter the subject's height and weight. The lab specific data is where you would choose between different marker protocols and different force plates setups. The last line here, the AnyMocap model, is something that should be left untouched. So it will simply load this generic MoCap model that will create all the model behind the scene. The model view here to the right is displaying, the 3D dynamic view of how the model looks like. And of course, it's possible to see this from different angles and so forth. And you can click on this model view, and it will take you to the model tree. And the model tree over here to the left displays the full representation of the model. So in this tree you can access every single variable of the model, and you can also go from the tree to the location in the script where this, let's say, a certain muscle has been defined. Up here in the middle here, there is a drop-down menu that allows you to choose between different operations that can be executed on this model. So this is where you can choose to do a parameter optimization of the model, that you could choose to do marker tracking or do the inverse dynamic analysis. This slide here displays a diagram of the operations that the AnyMocap model consists of. So the input to the model is this musculoskeletal template geometry, and it's some either static or dynamic capture trial. With this, we then do a parameter identification, and this is what this video here to the right is displaying. So by selecting the operation here in the drop-down that's called run parameter identification, the model starts optimizing starts being optimized. And what is being optimized is the segment length. It's the marker locations for certain markers, and so forth. So what you can see here on the video is that there are some markers that have green arrows displayed, and there are some markers that have red arrows displayed. So the green markers, they are allowed to move into another fixed location on the bone to provide a lower marker arrow against the measured data, whereas the red markers, which are typically associated with a bony landmark, they are not allowed to move. So the optimizer changed these marker locations, and it changed the segment length in order to get the best possible fit on the marker data. So that is then what is saved. It then saves these marker position and segment length into a file, and we can then proceed to the next analysis in this sequence of things that goes on. And the next set of analysis is sort of encapsulated in an operation sequence that is called run analysis, and that covers both marker tracking and and inverse dynamic analysis. So this run analysis is split into these 4 steps. So first, it starts by loading the parameters that came out of the parameter identification. Then it do the marker tracking, and that then saves the joint angles. And once that is completed, it then continues to the inverse dynamic analysis that then receives these joint angles and make the skeleton move according to the marker tracking. And it applies the measured forces to the feet and calculates what should be the muscle forces to create balance in this dynamic moving mechanical system. And then finally, it saves the output. So now we sort of come to the new models that we have released, and these models, they are based on Vicon Nexus sample data. So they cover all the different marker protocols and force plate settings that are displayed in this data set. And the aim for doing this has been to make it as easy as possible for users with similar setups to get started doing musculoskeletal simulations. The data set also includes tracking of external objects, such as, the golf club, a cricket bat, baseball bats. And for doing this, we have created a script that makes it rather easy to have such objects included into the model and being part of the dynamics. So the first example here I will show you here is a Gait model. So it's a lower body model. It's using the protocol plugin Gait lower body. The data set has 6 dynamic trials and 3 calibration trials, and we made models for all of these. It's using measured force plate data and apply those. And running this model will then, of course, it will then produce, calculate all the forces that goes on. And this is an example of how the output looks like in such a model. So here I'm displaying the activation of the soleus muscles in the right and left leg while he's stepping on those 2 force plates. And of course, this is just a glimpse of the output that is available. There's much more output available, including, of course, also the joint reaction forces and so forth. The next example here I'm showing is a Treadmill running cluster model. So it's on a Treadmill. So it's using a full body model, and it's a cluster protocol. It has there's one calibration trial which actually includes additional markers which are not part of the dynamic trials. So we have incorporated into these models that with a switch you can switch off these markers that is only available for the static trial, and then do this combination of then basically having two sets of markers for different marker sets for the dynamic and static trial. Also, what you should notice here is that, since it's on a treadmill, the ground speed is not 0, but this can be handled in this ground reaction force prediction class naturally. The next model here is very similar, except that it's using the plug-in gait protocol instead. Except that everything here else is the same. So yeah, it's predicting, the ground reaction forces, as you can see, being displayed by all these blue vectors when the person is touching the floor. The next example here is baseball. It's again using ground reaction force prediction. It's full body. It's using the plug-in gait protocol. Again, there is a calibration trial and 2 dynamic trials in the dataset. But it features a new thing here that I didn't show earlier. It's the optimization of some external objects. In this case, this baseball bat. So what we did here is that we roughly placed markers on the bat, and then we do an additional optimization of the location of these markers in a separate optimization. In the separate optimization, I will come back to that, how this is done exactly. But this allows us easily to incorporate external objects in the model and have their dynamics impact the model. This is similar, so it's showing a cricket throwdown model. It's doing ground reaction force predictions. It's 2 dynamic trials and 1 calibration trial. And again, also the bat parameters, so the location of the markers on the bat was part of an extra optimization. Next example here is golf. The setup is quite similar to the 2 previous ones. So again, it's a calibration trial. There is 2 dynamic trials, and we are also optimizing the location of the markers on the golf club. The next one here is a bicycle model. So here we're using the cluster marker protocol. And we had 1 calibration trial and 2 dynamic trials. And we are here actually optimizing a number of parameters related to the bicycle. So what we have done here is to create a parametric bike model which automatically adjusts itself to fit the marker movement. So we have done this by constraining the hands to the handlebars, the pelvis to the saddle, and the feet to the pedals. And then we use the optimizer to adjust the saddle position, the crank position, and the handlebar position in such a way that the marker errors becomes as low as possible. So it simply automatically fit the bike to the marker trajectories. And then, of course, we supply a certain crank torque to the crank, a resistive torque, and we allow the hands to have support from the handlebars and the pelvis to get support from the saddle. This is a very similar model, so it's just using the plug-in gait protocol instead. And finally, we have the table tennis example here. It's full body model. It's a plug-in gait full body protocol. It's doing the ground reaction force prediction to get the forces on the model. There are, I think actually there are 2 dynamic trials and 1 calibration trial. And I have to admit here that we have cheated a little bit. So the analysis is actually done separately. And then we have been using like a fixed camera in the model. And then the videos has been, stitched together. So the protocols that we have, that are being used by all these models is the plug-in gait protocol. So this has been This is part of this model library, and you can enable it with a switch. With one-line statement, you get this protocol. And there is the plug-in Gait lower body protocol, that can be enabled using a switch. And this protocol automatically enables extra drivers on the spine. So we always, to do the musculoskeletal simulation, we need to have the spine there. But of course, for this type of protocol, there is no marker information available for the spine. So we add in there artificial drivers that makes the spine follow naturally the pelvic movement. So by switching to that protocol, the model will automatically add those drivers, so you don't need to think about it. Then there is the cluster protocol that is shown here to the right. And as I mentioned earlier, it also has extra markers that is only available in the static trial. So those are, for example, what you can see on the knee and elbow, and those are can then be switched off with a single line. And you could then use the remaining markers in the dynamic trials. If you're using a different protocol, it's not a problem. It's quite easy to change the protocol to be different. It's a very flexible setup, and basically it just requires you to have enough markers to describe the degrees of freedom that are in the body model. And of course, the more markers you have, the better. And to define a marker, you need basically to use this template here that's called create marker driver. So it will basically, you have to give the name of the marker exactly as the name is saved into the C3D file. You have to tell the system where is this marker placed on the body. In this case, it's placed on the pelvis segment. It's also placed at an already existing node on the pelvic in the PSIS node. And we set here the optimization settings that it's okay that this marker should be optimized in the X direction and the Z direction, but it should be locked in the Y direction in this case. So this is the reasoning behind these green and red colors here. And that's basically everything that is required to create a new marker in a protocol. Then about applying the forces, it's easy. So we have these templates that with only a few lines of code, you can create the force plate, and currently we have support for type 1, 2, 3, 4, and 5. And using that template will simply create the force plate as you see it here in the slide, and it will automatically hook up to and you will have to, as part of doing that template statement, you will point at the data in the C3D file, and then the force plate will automatically retrieve those data, add them to the force plate, and ensure that they are transmitted to the feet. So it will also automatically place the force plate in space using the corner information of the plate that is part of the C3D file. So it's really only a few lines that is required to define such a force plate. In a similar fashion, also the ground reaction force prediction only requires a few lines of code, and it will it will create the contact between the feet and the ground. Yeah. Now come back to this external objects that I mentioned earlier. So we have, in the examples I've shown you, we have incorporated these external objects like the cricket bat, the golf club, the bike model. And we have tried we have tried to make this as easy as possible. So we have sort of hidden away we have hidden away in a shared file some of the common stuff that needs to be done, so that you don't need to care about it. And the only thing you need to do is to provide some initial guess on the marker location on this object that you're adding to the model. You have to, of course, also specify what is the mass and the inertia properties of this object that you are adding, and you have to decide on some visual representation of the object. And in this case, with the golf club, I simply just created two lines of different thicknesses, but you could also include easily a CAD file to represent the visual appearance of the object. Additionally, in case of the bike model, you will also need to specify the crank load, how much load you want this subject to apply to the pedals. So by including this external object, it will automatically add this extra parameter identification step into the analysis pipeline. And so this analysis will happen after the first parameter identification that was created, that was done on the human. So after this one here, the human is fixed in size, and then we move on and optimize the parameters associated with the external objects only. And then these parameters are fed into the marker tracking, and also what comes out of that now is also then the motion of this external objects, which is then fed into the inverse dynamic analysis. So this object will follow through all the steps now automatically. And as a user, really, what you have to specify is just the marker location, the mass inertia, and the visual representation. So that can be used in a generic fashion to create objects that the person is moving around, basically. It also handles that the forces are transmitted from either both hands or one of the hands to this object, as you decide. We also, as part of this library that we made available, we have created a processing script. So it's based on Python, and there is a file there called batchprocess.py. It's based on AnyBody tools, and it allows you to run the AnyBody console application in a batch mode to process all these models and do this in an automatic way. These models, they are available on GitHub now, and they are to become part of the AMMR that comes with AnyBody. And these models have been tested with the AMMR, the current version of the AMMR models to 2.44. And this is how the GitHub model repository landing page look like. So how to get started using your own data? It's to simply, get this repository, make a copy of the model in that repository that resemble most your lab settings, and then follow the instructions that is available on the GitHub page. So what I want you to take home is that it's quite easy to use Vicon C3D files in AnyBody. We make this repository available to make this as easy as possible. If you want a trial license, send us an email. If you want a meeting, send us an email. So that concludes my presentation. Thank you very much.
Thank you so much. I can see we've already got questions coming through, so I'll get started. But if anyone else has any more questions, feel free to add to the chat or Q&A. So the first question is it possible to run AnyBody models on the video captured with two cameras with minimal markers, for example, targeting knee joint?
It depends. So then you would need sort of to cut away, the part of the model that is not part of, that you don't have markers for, or you need to create synthetically the movement of those body part that was not measured. And you would need also to have, supply the model with measured forces. So then it would not be possible to do predictive ground reaction forces. For that would require the full body motion to be recorded. So generally speaking, it's possible, but it depends on the exact situation.
Next question, are there any models focusing on orthopedic patients, how these models generalize to patients after surgery?
I mean, no, I mean, but you would be able to. I mean, since this is, I mean, the models are based on a scripting language, so you have access to every single part of the model. So that if through that surgery that's been, you know, made modifications to the musculoskeletal structure, it's possible then to go and change specific parts of the model as needed.
Thank you. Is there current capability to track segment motion using IMUs, or perhaps a line to incorporate this in the future?
I mean, usually IMU data goes into the model through a BVH file. So many of those systems, they can export their motion data as a BVH file, and we have a BVH file reader that can read those files. And in fact, the AnyMocap model also has this built-in capability of being able to read BVH files. And much of the pipeline I showed for this model I showed today is very similar for a BVH file that is typical format for IMU data.
Thank you. I've got a couple of questions about validation and documentation. Is there a place on the website where people can find more of the publications and validations of the models that are available through AnyBody Technology?
Yeah, so I displayed this. I mean, there's this publication list on our webpage that has this list of papers being categorized into different categories, and one of them being validation. So that will give them sort of the list of the papers relating to validation of some kind. So really comparing model data, model output against measured data. In terms of documentation on the model, there is a model documentation page also available on the web that displays. I mean the different settings available in the body models and many of the references that has been used to create these body models.
Thank you. Next question, is this limited to humans?
No, I mean, you can model any sort of living creature. So, but we do not provide sort of a lot of examples for other type of animals, but anything with a musculoskeletal structure you can model using this tool. So you can just create your own model bottom up. And there are indeed, I think, on our publication list, a number of examples on animals. I think there is a tab for animals, and you can see examples of people that have been doing exactly that.
Perfect. Next question. I'm wondering about hand grasps in the sports models you showed. How does one measure, for example, grip strength?
Yeah, so actually I cheated a bit in these models. So I simply put a reaction force between the hand and this object, and I didn't do a proper grip. Also, this marker data set didn't contain, I mean, the grasping motion of the fingers. But we do actually have a hand model available that can do a grip in different ways, but you have to drive really the movement of the fingers then.
That's great. Next question is to do with the cervical spine, and does the facet joint get modeled as well?
Yeah, I'm not sure if they're available for the cervical spine, but for the lumbar spine, it's possible to enable facet joints. Yes.
Next question, well, a question and a comment. Thank you very much for the presentation. Let's consider a gait trial. Would it be possible to set a specific posture for a subject, for example, through the angles describing lordosis, what is not derived from the markers?
Yeah, so you could overrule, you could say the markers and impose, additional drivers to the model. That is not a problem. So you can let the markers decide on certain part of the body movement and then impose extra motion drivers as you want.
Perfect. There's a couple more questions. Is there a capability to include internal objects such as implants into simulations similar to external objects?
Sure, that is possible, and there are examples of that on our website.
Final question, I believe, because no one others are coming through. This again is a comment as well. Greetings, I'm presently working on Vicon Motion Capture system for lower extremity rehabilitation. Is there a possibility to try AnyBody software on a trial and validate the effectiveness of the integrated system? I believe you've already answered that in the previous slides. So you just need to contact the email address to, if you could go back to the previous slide, I think that'd be fantastic. Yeah. So that's where you need to go. So those are interested in more information or a trial license, sales@anybodytech.com. There is one more question, and we'll finish on this one. Do you have a version of software without any scripting?
So no, without any script, no. It always requires you to write some script. That being said, really, I mean, models driven by motion capture data is really, we really try to make it as easy as possible with a minimum number of changes to run these models. So it's not that you basically you can load these you can load these generic models, and once you sort of learned your way around in these models, it's not a lot of scripting that you need to do.
That's great. Well, that was all the questions. So Alicia, I can hand over you to end the session. Thank you so much, AnyBody Technology, for joining us.
Thank you.
Thank you everyone else for participating and listening in.
Yes, like Kim said, this was a great session. Thank you so much for joining us. You can always send questions to info@Vicon, marketing@Vicon, about any upcoming events. Make sure to follow our social channels. And then this recording will be sent to your inbox in the next 24 hours and is also on YouTube now.